Welcome to chapter 5. So in this chapter we'll talk about electrical energy and current. So in this chapter we'll see 4 different parts. So in the first lecture we'll discuss electrical potential and capacitance. In the second lecture we'll talk about current and resistance and electrical power. So let's start with the first section, electrical potential. After you complete this lecture, you should be able to distinguish between electrical potential energy, electrical potential and potential difference. You should be able to solve problems involving electrical energy and potential difference. You should also be able to describe the energy conversions that occur in a battery. So let's start with electrical potential energy. So what is potential energy? Potential energy is the energy due to the position. So sometimes if you talk about position here, so by virtue of position here, if the position is height, we call that gravitational potential energy. If that position is elasticity, we call it elastic potential energy. If that position is electrical charge, we call that electrical potential energy. So remember that potential energy is energy that comes due to a field. Here field energies that we generally know about are, one is the the two electric field energies that we generally see are electric potential energy and gravitational potential energy. Now electrical potential energy is the potential energy associated with a charge due to the position in an electric field. Remember the term position. So if the position is height in a gravitational field, we call that gravitational potential energy. Here the charge has a position in an electric field. Just because it has its position in the electric field, it does have energy. So the electrical potential energy is the component of mechanical energy. So when we calculate mechanical energy, total mechanical energy of any body, we calculate it as kinetic energy plus gravitational potential energy plus elastic potential energy plus electric potential energy. So this is the total mechanical energy of any given object at any point of time. So this electrical potential energy is associated with a charge in a uniform field. So the electric potential energy in a uniform field is given by the formula potential energy electric is equal to minus Q times ED. So Q here represents the charge, E represents the electrical field strength, and D here is the displacement from the reference point in the direction of the field. What does that mean? For example, let's say if you have a certain charge here, let's say I have a positive charge here. Let's say I have a positive charge here. So this positive charge has its own field. For example, let's consider that this is the field of that electrical charge. Now this charge, whenever you bring a test charge, for example, let's consider there is a test charge here, Q. So you need the energy that this charge gains when this goes from outside into the field. The energy that it experiences at this particular point is called as the electric potential energy. So the energy that it experiences, either attraction or repulsion, we call that electrical potential energy. So this here is the idea behind potential energy in terms of electrical energy. Now how do you calculate the electrical potential energy is by using the formula P electric is equal to Kc times Q1 Q2 by R. So Kc here again Coulomb's constant, Q1 and Q2 are the charges that you are trying to look at, and R is the distance between them. So electrical energy is Coulomb constant times charge by distance. So next let's talk about potential difference. So we talked about electric potential. Now we want to talk about electric potential difference here. So potential difference is the amount of energy per unit charge. So the amount of energy that you require per unit charge is given as electric potential. So electric potential equals the work done that must be done against the electrical forces to move a charge from a reference point to the point in question divided by the charge. So how would you imagine that? For example, let's say you have a certain charge here and this charge has a field here. So let's say there is a test charge here so there is a test charge Q, the amount of energy or the work done that is done on this charge from bringing it from outside into this field, right, where you're putting it at a point R from the field, is called as the potential. So potential is given by the work done, electrical work done by the charge, and we can remember that work done here is equal to the potential energy, so it becomes electrical potential energy by Q. So this is the formula for V here. So we already know that electrical potential energy is minus QED by Q becomes QQ gone, so V equals minus ED. So this is the formula for potential minus E times D. So we can remove the negative symbol anytime we want depending on the reference charges that we use. So V generally is written as ED. So V is generally written as ED. Now potential difference here is a different question. Potential difference is the work done when you're moving from one point to another point inside the electrical field. So what does that mean? For example, let's say we have a charge here. So let's consider that this charge has a field here, and you have a test charge at a point A, and you have to move that to another point. So you have to move it to another point B. So the distance here, so remember that at this point there is a potential VA, and this point there is a potential VB. So here potential difference, the name itself says your answer. So potential difference is written as delta V equals VB minus VA. It's the difference in the potential between the 2 points. So it can be written as WB minus WA by Q, or potential energy electric at B minus PE electric at A by Q. Or we can simply write it as delta V equals delta PE electric by Q. So this is the formula for potential difference, and this is generally the formula that we use to calculate the potential difference. So potential difference can also be written as delta V equals minus E times delta D. So delta D here represents the distance between the 2 points. 2 points A and B. So V here, vector V here is a scalar, so which means that there is no direction involved. So we do not need to write any direction for potential difference. So this is the formula, delta V equals minus E times D. So let's try a problem and let's see if we can solve this problem. So it's given that a charge moves a distance of 2.0 centimeters in the direction of a uniform electrical field whose magnitude is 215 Newton per coulomb. And as the charge moves, its electrical potential energy decreases by 6.9 times 10 to the power negative 9. So delta potential energy electric is decreasing, meaning that it's negative. So negative 6.9 times 10 to the power negative 19 joule. So they are asking you find the charge on the moving particle and what is the potential difference between the two locations. So first things first, so it's already given, distance is also given here. So D here is 2 centimeters. Now using this, now what can we first find? So first let us find the voltage. So delta V, you know, is minus E times delta D. So delta V equals minus E value here is 215. So 215 times D here is 2 centimeters. Convert it into meters. So it becomes 0.02 meters. So now you get minus 215 into 0.02. So 215 into 0.02 becomes 4.3 volt. So volt here is the unit of electric potential. Remember this unit. is volt. So delta V is negative 4.3 volts. But we also know that delta V is potential energy, delta potential energy electric by Q. So we want to find Q here. So Q goes here, delta V comes here. So you get delta potential energy electric over delta V. So delta potential energy electric is minus 6.9 times 10 power negative 9. So minus 6.9 times 10 to the power negative 19 over delta V here is minus 4.3. So minus minus gone. So you have 6.9 divided by 4.3, that becomes 1.6 times 10 to the power negative 19 coulomb. So this is the charge on that particular value. So this is how you can solve this problem. So they also asked us, so first find charge, and they are also asking us find potential difference. So we found this is the potential difference and this is the charge. So we found both the answers, right? So we found both the answers. Now let's continue our discussion on potential differences. Now, so at right, the electrical potential at a point A depends on the charge at point B and the distance between the two charges. So the distance between the two charges and the position at where it lies. So an electrical potential only exists at some point in an electrical field regardless of whether there is a charge at that point. So remember that any electrical potential will always exist in an at some point in an electric field regardless of where there is a charge at that particular point. So even if there is no charge, it means that there is a potential there. So the reference point for potential difference near a point charge is often given at infinity. That value is written as delta V equals Kc times Q by R. So this is the formula that we use to write the potential difference for any given charge, any point charge. So Kc again, Coulomb's constant times charge by the distance to the point charge. So we use the superposition principle to calculate the electrical potential when you have a group of charges. So again, how do you use the superposition principle? Use the same principle again. Try to calculate each value and sum up all the values. So delta V here becomes equal to V1 plus V2 plus V3 plus V4 and so on. So depending on the number of charges, we will just add it up, and the sum of all the point potentials becomes the total potential at that particular point. So with that in, pause the video right here and try to solve these problems. So next let's talk about capacitance. So after you complete this lecture, you should be able to relate capacitance to the storage of electrical potential energy in the form of separated charges. You should also be able to calculate the capacitance of various devices, and you should also be able to calculate the energy stored in a capacitor. So let's start with the capacitor. What is a capacitor and how does it change its difference from batteries? A capacitor is a device that stores electrical potential energy. A battery is a device that stores electrical potential. So there is a difference again, a slight difference, because remember that this is actually storing energy. Capacitors actually store energy, but batteries they already have chemical energy. So they convert chemical energy into electrical energy, but capacitors by their nature store electrical potential energy. So capacitance is the ability of a conductor to store energy in the form of electrically separated charges. So how are we storing energy here? We are basically separating the charges, positive and negative, separately, and we are keeping them that way until we need to utilize those charges. So the energy, the SI unit is farad, and which it equals coulomb per volt. So capacitance is the ratio of potential, the ratio of charge to the potential difference. So capacitance here is the magnitude of charge on each plate by the potential difference. So this is an example of a capacitor when it does not have any other, so when it is not working or when before it is charged, right? So once you start charging it, what will happen here is that all the positive charges will try to move towards the negative charge of the plate. What happens in the capacitor? Let's consider that this is the negative charge of the plate and this is the positive charge of the plate. Once you start creating, remember that there is nothing, so there is space between the two plates. So you're not actually connecting the two plates, you're actually keeping the plates separate from one another. So once you start connecting this battery, so once you start connecting this, what will happen? All the positive charges will start going towards the, so all the positive charges here will start going towards the negative plate of the battery. So they want to go towards the negative plate of the battery, and all the negative charges here will try to go towards the positive plate of the battery. So once they move, what will be left? So you just have positives on one side and you have negatives on the other side. So this here is the process of charge separation. So this is the process of what we call charge separation. So we call this charge separation. Once charge separation occurs, what do you do now is once it reaches a certain point where every charge that is left on one side will go towards the other side. So what do you do at that point is basically remove the potential from the battery. So we are basically gonna cut this cord. Once you cut this cord, now everything that is already present there will stay as it is and will be left like it is. So now what will happen here? The ones where there was negative charge, the plate that has negative charge will be negative charge. The one where positive charge will stay as positive charge. So once charge separation occurs, this is the point where we say that this particular capacitor is charged. So this is where the capacitor is charged. So what we do now is we can use this charge and connect it to another device. For example, let's say another device, for example a load, and once it releases the load, what will happen now? It will complete a closed circuit where the negative charges will flow towards the positive charges. When this movement occurs, what will happen now? This creates current. This creates current and the charge will flow towards the one plate towards the other plate, and that position is called as discharge. So capacitors work on the principle of charging and discharging. So during the charging phase, they store potential energy. During the discharging phase, they release the potential energy to use it for purposes. So what are the factors does capacitance depend on? Capacitance depends on two factors. One is the size of the capacitor and the second is the shape of the capacitor. So it's given by the formula C equals epsilon naught A by D. So this is the value for C here. Capacitance is epsilon naught times A by D. So epsilon naught here is called as the permittivity of vacuum. So it's a constant. The value is 8.85 times 10 power negative 12. A here is the area of the plates and D is the distance between the two plates. So the problem with increasing the capacitance is that can we maximize the capacitance of any given device? The only way you can do that is either we will have to increase the area of the plate. When you increase the area of the plate, you are basically increasing it too much, and you have to decrease the distance. So when you decrease the distance, then capacitance will increase. But when you bring it too close, there is a chance that the device will break. So what you want to do now is there is one other method of increasing the capacitance is by using a material between the charges, between the capacitor plates. So that material can help change its capacitance. So we call that a dielectric material. So that material that we use is called as a dielectric material. So what is this dielectric material? A dielectric material is basically an insulator. the better the insulator, the better the capacitance of that particular capacitor. So what is the use of this dielectric material or the insulating material here is that whenever we have the two plates, there is what we call dielectric interactions, where one plate tries to attract the charges on the other plate, and this causes a small decrease in the electric field. So the effect of a dielectric here is to reduce the strength of the electric field in a capacitor. So by reducing the strength on the electric field, it can store the charge longer and separate. So best example of a capacitor is your keyboard. Whenever you press your keyboard, you're basically using this capacitor. So when you press it down, the key attracts, so there is a dielectric material, and the dielectric material will go down. There is a change in the electric field. That change in the electric field in your computer is calibrated to movement or data. So one of the most common plates is in a parallel plate capacitor, where we have two parallel plates connected to, so two parallel plates separated by a distance d, and each plate having an area A. So these are two rectangular plates, and there is no net charge on a plate whenever you take them. Now how do you calculate, so what is the potential energy stored? So the potential energy that is stored in a charged capacitor, it depends on charge and the potential difference between the two plates. So that is given by potential energy is equal to half Q times delta V. So half times charge on one plate and final potential difference. So the product of all these values becomes the electrical potential energy. Now let's try a problem and let's see if we can solve this problem. So let's see what is given in the data. So a capacitor connected to a 12-volt battery holds 36 microcoulomb of charge on each plate. What is the capacitance of the capacitor and how much electrical potential energy is stored in the capacitor? So the two data is given. So Q, which is 36 microcoulomb, so which can be written as 3.6 into 10 power negative 5 coulomb. Next, unknown values are capacitance. They want to find capacitance and the electrical potential energy. So now let's try and calculate the capacitance. So what is the formula for capacitance? So capacitance C equals Q times delta V. Sorry, Q by delta V. So substitute the values of Q and delta V. So what are the values that we have? Q is 36 microcoulomb, so which is 3.6 times 10 to the power negative 5 over delta V is 12 volts, so by 12 volts. So if you calculate, you have 3.6 times, so 3.6 divided by 12, that becomes 0.3. So 0.3, so this value entirely when you calculate, it becomes 3 times 10 to the power negative 6 farad. So when you have negative 6, it's micro, so it becomes 3 microfarad. So capacitance is 3 microfarad. So when you have the potential energy, the electric potential energy can be written as half times Q times delta V. So half times 3.6 times 10 to the power negative 5 times voltage is 12. So you have 3.6 times 12 times 0.5. So that becomes 21.6 into 10 to the power negative 5. So when you substitute correctly, you should get 2.16 into 10 power negative 4 joule. So this is the electrical energy that is stored in the capacitor. Now pause the video right here and try to solve these problems. So with this we end lecture 1. So I'll see you again in lecture 2.